Just let me know.
Okay, let's begin. Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Mr. Shailesh Ghotgalkar, and he will be speaking on real-time control, a performance perspective. Mr. Shailesh Ghotgalkar is the Product System Manager of C2000 Microcontrollers business at Texas Instruments. He is an accomplished chip architect and design leader with 25 years of experience in defining and developing products from marketing requirements to production ramp across personal and mobile electronics, industrial drives, electric vehicles, and digital power supplies. He has contributed to 3 product roadmaps, 15 device definitions, 22 plus tape outs at Texas Instruments. Prior to Texas Instruments, he was with CDAC and responsible for development of first 2 reconfigurable computing systems platforms from concept to user deployment. His research areas include low power, low cost device architectures, control optimizations for industrial and automotive applications. He is recognized as a senior member of technical staff at Texas Instruments and is also a senior member of IEEE. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Mr. Shailesh directly after raising the hand. Over to you, Mr. Shailesh.
Thank you. So, good evening, and thanks for joining this session. So, I would like to thank for the opportunity given to me to present this. So, I'm going to talk about the real-time computing as a performance perspective. So, in this strange worlds that we are living in, and especially after this breather that we got after the pandemic in last few months, or about 6 months or more, so or about a year or so, we have seen that there is a spurt of increase in computing requirements, and where many standard initiatives which basically were even before the pandemic or through the pandemic were there, are getting started with the new vigor. And it is in factory automation, building automation, green energy, and so on, many different fields. And what it has caused us is to give a high performance requirements rising rapidly. And there are different processing requirements that are coming out of different applications. What we are going to see today is real-time control requirements. And we're going to do a comparison with the other type of applications. And the talk will be primarily focused on the real-time control, but you will also kind of get a vis-a-vis comparison with other applications and how what performance means and how basically it gets compared. So let's get started. Here is the agenda. We will first go through the what is the real-time control. And we will also look at what are the related end equipments and applications. We will look at what are the new trends in these applications which are actually driving those requirements for real-time control. And that would be kind of divided into the 3 pieces of the real-time control, or 3 portions of the real-time control. And then basically we will do a comparison with the other application needs, a little bit of a summary of how it can be addressed in the real-time control. And then we will summarize. So what is the first thing is what is real-time control? Okay, so let's get started. Now, if you really look at in general, the energy conversion field, then there are multiple ways in which the energy gets converted from one form to the other, and different forms of energies, right? While doing this, there is always some underlying physical system. And that system is modeled mathematically as a function of time. And when you take such a system, and the system that would need a response time which is the shortest and predictable from the time you sense the input, from the time you sense the input till basically you apply back it to the actuation or to the underlying system. That system is called as a real-time control, and the emphasis here is on the shortest predictable latency, and that will drive the need for optimizing the overall latency of the path and predictability of it. And this can be broadly divided for the real-time control into three pieces. First piece is the sensing, of course, the processing and the actuation. So this particular thing, what we are trying to do here, we are trying to complement the behavior of a plant with something that basically is modeled in our system as a plant. And based on sensing, we are actually re-evaluating that model and creating the actuation signal which gets applied as a PWM or any other sort of requirements that you have in the system. So that is the basic of it. So what actually it means that as quicker and faster you are able to do it, as much you are able to compress it, you will basically be able to do a better job. And while doing this, you have to make sure that one run to the next run, or between the two similar type of applications, you have the latency that you get should be predictable. Now, this is very commonly used in multiple industrial as well as the automotive applications, energy conversions, and so on and so forth. And there are new rising requirements in each of these, and we will look at it in a subsequent slide. So before that, we'll look at what are the applications. When we talked about the applications, just to give you the feel about what are the applications. Just take a case of power generation. What is today we are looking at is there are very many environmental resources that we have, and from that we extract the power. So how do you extract the maximum power? That basically is the goal. And in those power generation applications, real-time control is quite critical. Then power conditioning, all type of supply conversions is take AC and DC as two base types and all the four combinations of it, right? DC DC, DC AC, AC DC, and AC to AC as well. So all these combinations, if you look at, and each has got different type of applications, right? And more and more sophistication you need as you go for some of the recent system requirements and application trends which are coming in there. Similarly, the automotive, which has caught up in last about 5 to 10 years, I would say 7 to 10 years, I would say, is driving primarily the requirements for the main powertrain control, as well as the source of the energy to be harnessed with the batteries in the automotive. So for both of these applications like traction control, onboard charging, DC-DC, those need these applications. Motor control, conventionally for many years now, more than maybe 100 years probably, is the one which is the basic behind which is I would say the originating point for the real-time control, and all different types of motors, and every year you get different types of motors in the market, small variations, different ways to control, and all these basically would drive the similar requirements. Underlying thread is the same: shortest predictable latency that you need to get out of it. And of course, industrial drives is a very common application of the motors. Difference between the drives and a motor control, if just for from a very broad perspective, is in one case you're looking for just to run the motor at a given RPM, given torque, and so. Whereas in the second case, you're looking for a very precise control of the motor in terms of wherever you're employing it, right? So these are different applications which are today addressed by the real-time control. Now we will look at some of those trends in those applications and how basically those are driving some of the requirements. Take a case of energy generation and renewable sources. Now, conventionally, we used to have the thermal power stations or have basically the hydroelectric power stations. Now, more and more emphasis is on green energy. More and more, people want to kind of optimize the energy coming out of solar or wind, and this energy that is coming out of these sources is not very constant. It's quite variable depending upon the conditions in the nature, and how basically you can harness that to the maximum is the biggest thing. So like for instance, if you're doing the solar, you have to have a MPPT algorithm running behind it. At the same time, you need to ensure that all your the number of panels that you're connected have got like anything that is going wrong in it is kind of detected, isolated, made sure that at no point of time the line condition or wherever you're feeding the if you're directly connected to onto the line or through the grid, you basically have the conditions maintained there, or you get out of the grid, right? So all these basically are driving. Of course, there are a lot of new applications coming in a transmission and distribution, especially with miniaturization of the components involved in the transmission and distribution, and going as much as kind of lighter and smaller kind of distribution stations, and the transmission stations and so on, right? So that basically is one part which is driving. So what are the trends that are impacting the control from the control type? Basically being able to kind of work with the different environment conditions. B, basically you are able to kind of get a smaller and more optimal control out of the newer techniques and topologies that we have. The second thing that we have seen in past few years, and which is more and more growing very rapidly, is in the energy distribution, and most of it now getting focused on how do you store the energy, and how it can have a battery based backup. And it is across the residential, factories, or even for the EVs, and of course for the green energy that we talked about. In these conditions, it's quite critical that how do you well manage the battery pack of battery supplies, ensure that the output that you have is quite stable out of it, and there is a highest efficiency because you'll be going through the multiple stages of conversions from the original source where you receive. Say if you're receiving it from line and you've got a wall power kind of a power wall kind of application where you're storing it at home with on some batteries. You've got one level of conversion and then you're taking it back. In all this conversion, how do you eliminate the losses and get the highest efficiency? That is basically that is the trend which basically driving it. And apply it onto the automotive, you would see that range problem where basically range anxiety, how much I can drive with a single charge, and so on, right? All these are basically the extension of the same underlying problem. And of course, in a conventional type of motor control, and in the motor control, there are two types again, industrial and automotive. In an industrial as well, the more and more requirements of automation, more and more multi-axis drive controls, and the more higher precision on the position and a speed, given that the robotic controls that you have in a factory, because there as well you want to improve the efficiency of your production, which means that the robots need to be efficient. Those not no wastages, the precision has to be higher. And that basically is driving many of the controls, especially like some of the standards like Industry 4 have a lot of emphasis on having basically the a similar type of interface, so that then there is that brings a scalability angle to it. So all of these have got some or the other implications on what actually performance on the real-time control means. And of course, on the automotive side, we have there is a continual research that is happening on different ways to optimize the motor size, because that would add to the weight. At the same time, how do you get to the best efficiency of it, get to the highest RPMs, where earlier in the industrial, probably you would go 10,000, 20,000 RPM or so, but now basically people are going above that, going up to 30,000, 40,000 RPM, and these basically are quite a kind of a, not only just with the conventional motors, but new type of motors and different variability of your variability in terms of a torque or in terms of the speed requirements, because depending upon where you're driving, how you're driving, and so on. So these basically are some of the different challenges at a high level, which basically are driving some underlying requirements, which we'll see in a few minutes from now. So I just want to now take this onto the different side. What is happening while these applications are driving in certain direction? What is happening on the side of system side, right? And this is one of the graph from one of the paper in the power semiconductor devices person has taken it. There are three primarily the graphs that you see here, or three primary lines you're seeing here. One is what is happening on the device side, and what is happening on the optimizations on the controller side, and the and basically the switches side. You take the cases where basically you have basically the wafer or a foundry, how they are moving in a years. Then the devices which we are and the controllers for what we are creating for that, how fast they are moving. And then basically if you take a case of the tools and basically the equipments that you're using in this application, where they are driving, what you can really see is over the last few years there is almost 5x increase in basically in basically the power density that is happening. At the same time, there is the movement of the of the switches, or in terms of the where the performance is going, has not really moved that fast. But then there are the overall efficiency or the optimization that we are achieving is with the combination of the controller, the switch, as well as what can be done at the system level or at a board level, those optimizations. So the combination of that is always is driving it. Of course, there is a fast-paced research today with the wide bandgap switches of the GAN and basically the SiC, those have come, and which is driving higher switching speeds and also giving a higher voltage range. The losses are quite low. Of course, the emerging applications are really pulling the that demand of higher speed, higher switching speeds and higher voltage range, which is definitely getting absorbed there. So it's really an exciting time in as far as the solutions are concerned for the problems that we were talked about. So if you kind of look at it from the one more level deeper, as we talked about, this is kind of an example which is showing this is actually a server power supply kind of a break, and it shows that how basically the power density has kind of gone down in terms of it's almost a 5x that it has reduced. At the same time, on the energy efficiency side, we are inching like by every percentage, a percentage or a fraction of percentage with variation in the load. Like for instance, now we are pushing the envelope on the load side, go to the 90% load, 95% load, but still give the efficiency which is 90 plus, right? And that's something which basically was not something thought of if you go about 10 years back, or about yeah, even for that matter 7 years back, right? And this is something which is quite interesting. So what it brings to the controllers per se, or how does it at a system level it would come. Our goal is to get higher power density, higher energy efficiency, and certain applications also need a faster transient response. So of course, when you're talking about higher power density, you need a smaller area. and smaller size of the magnetics and the as in coils, the capacitors, and so and which is possible with the increase in the switching frequency. And to increase the switching frequency with the conventional switches would tend to the higher losses. So naturally, that is where the wide band gap switches use of that will come. At the same time, as far as the controller is behind it is concerned, while you're increasing the switching frequency, the processing or the megahertz for the controller that you have also needs to go high, which is more power. So what you need to do is to avoid this higher megahertz. Can you keep the megahertz lower and still being able to do the meet the same frequency? And then basically you can have multiple techniques. You can have accelerators, you can have hardened state machines, or build a custom data path, and so. And that basically is possible, right? But that is something which is a knob that you can use to get it there. At the same time, your actuation has to be improved in terms of how you're controlling it, what is the resolution, and so effectively that would lead to your reduced losses, be it the switching losses, be it the losses because of the limit cycle oscillations. If you don't have the right amount of resolution, we'll look at what actually it means in a subsequent slide. And then basically we have it will overall give us reduced losses and bring in the energy efficiency. At the same time, if you have got a faster settling and better a higher switching frequency and a performance, it would also address some of the requirements like a faster transient response. Now, that is in a nutshell what we are trying to look at, as in how that is done and how that differs with the other conventional applications. Okay, I would like to kind of go to one more trend apart from this. Something that is what we saw so far is a very much related to the core real-time control. But there are other factors which are also coming into the system, which are driving some of the trends, and those are basically things like the safety. And so to get basically the get basically the application built with a reasonable or lower risk at where basically you are able to detect and diagnose within certain window or within certain time. That sounds like a very naive definition, but that actually brings in a lot of performance requirements, because now every node or every basically the component that you have in a system needs to be observed. It needs to be continuously kind of diagnosed, and then basically you are taking a call as to whether basically I'm going to put an override, or I'm going to allow it to kind of go ahead, right? And of course that actually brings in a very high requirement in terms of the millions of instructions per second. If you and this is basically very generic concept here that I have used of a MIPS. It's a little different than what you basically would think in the conventional applications, but I have made it generic for just giving this thing. And when I say it's a generic, say that everything that we talked about on a real-time control and other requirements that you're seeing on a slide, if we are able to do this, then how much of that and say convert it into some kind of a megahertz for the controller, how much actually you will have to set aside for the safety, and that is quite significant. It's about 30 to 40% of the overall MIPS that you have on the chip, right? Similarly, the security attacks and basically the data security as well as the security of the code, this basically is under that area is under threat, right? And which is requiring a newer type of accelerators, a newer type of hooks, more convoluted ways to kind of store the data, send the data across the systems, and so. And that basically means that you have to apportion a separate set of MIPS, if so to say, in here. Now you can follow different ways and build their own accelerators, the separate engines to do it, the state machines, and so. and solve it. But the problem is that once you go something custom, you are outdated. Within few years, your part is in market, and if it is hacked, or if it is kind of somebody is able to crack that code, the way in terms of whatever data you're transferring or whatever the algorithm that you use, then basically it's not useful. So it means you have to also apportion extra performance of the MIPS on chip to get basically the something called as a crypto agility, where you are able to kind of if certain thing is cracked, you are able to kind of support it with the CPU on a system, and still being able to be relevant for that application. Besides that, there are other requirements which are basically these systems of a real-time control. They need to work across the environmental conditions, be it the temperature, humidity, EM interference, and so. Just to give one example, right? And this is something which basically is all the industries today struggling as far as the microcontrollers or MPUs is concerned. There is a very high need in terms of the a flash or the memory, that basically non-volatile memory on the chips, and that's basically because there is a need for a faster time to market. People want the automated design flows. They're using tool-based system designs, and most of you might be also doing it. Use basically MATLAB and generate the codes directly and use it. Sometimes because of all of these tools are kind of trying to generate it from some generic framework, there is it's not the optimized code the way one expert would do and sit basically and optimize it, right? So naturally the size of memory is increasing, and if you look from the technology perspective, as in the wafer technology perspective or the semiconductor technology perspective, we are now going on to lower and lower nodes, and beyond certain point, like for instance beyond 28 nanometer, we do not have the ways to store the NVMs, which is NVM is not charge based. It actually you have to have some different techniques. So memories like MRAM and so are coming, but the problem is when the magnetic RAM comes in, it has to be working in all these environments where you are always surrounded by coils and motors and so, right? So that brings another set of problems in terms of how you do it. Now that exactly not directly related to the performance, but the problem is that if you are not able to provide enough NVM on chip, you have to go outside. It means that you have to use an engine to kind of pull the data, pull your code fast enough, and so on. So that eventually brings in indirect kind of thrust on the performance requirements. So there are basically these are some of the trends which are driving and requiring basically the newer things. Now I'm going to go a little bit deeper on these requirements, and maybe all this sensing, compute, and actuation I'll talk about. But before that, I will briefly touch upon how conventionally you look at the performance requirements. Okay, so if you look at the conventional performance requirements, I've taken few kind of a representative applications here. And what are the common parameters? Like for example, you take client server class processors, right? The major or a key there is the megahertz of the CPU, with the CISC CPU mostly, and what are the amount of MIPS available. That would be of essence. In some applications, there will be a degree of parallelism. You take a networking applications, there is a degree of parallelism. How many sessions or contexts you can simultaneously service, right? And that basically that decides basically the performance of that system. Or take basically even that is also applicable to some of the graphics and the AI engines, where how well you can do the things parallelly with some custom kind of a processor, right? So that makes basically the requirements of that application. In many of the networking, as well as these other applications I talked about, throughput of data which is transacted or transferred online, that is one of the parameters. Of course, latency of response is a common thing, but again, this may be very parallel to what is real-time control, but comes back to that shortest predictable latency that you provide, and it is basically in some different terms or in some different avatar. You will see that in different applications, but it is still within the in some sense of some microseconds or milliseconds or so, right? But that is something which it will come back to. Of course, the whether the performance that you are adding, is it scalable? Can you just add another server card? Can you grow that? Basically, how well you can grow that basically is another factor in certain other application when it comes to similarly the megahertz per milliwatts, what is or milliwatts per megahertz, which basically you take either ways, right? Those are the parameters which are today kind of increasing in terms of all the battery based, the coin cell based applications, and even for the some of the conventional battery applications that we have seen. And on all top of that, I think the common factor in all the applications is size and cost of the solution. Now that basically is a leveler, and that basically would bring that you may have a very exotic solution, but ultimately it will be bound by the cost, and at times it will by the size. So one thing that is different in terms of the real-time control is we do not have so much emphasis on a power. We have emphasis on power, but in most of the cases where you have wall-powered controllers, it's not like a low power kind of applications that basically we talk about. Of course, the power becomes important by some other factors, as I talked about, as in power density. If you're putting it in some kind of a server power supply or a power supply of say telecom rectifier, there basically the power of the controller itself becomes quite important, but not to the degree of where when you are on some coin cell battery or so, right? So those are some of the differences in there. So what we do is we now go into a little bit next level of depth of or basically go to the 3 layers of requirements from the real-time control application. Now, first thing is on sensing. And when it comes to sensing, the very important part here is that how much is the resolution of your application, and that's very key. And that would basically decide the type of applications you can serve or you cannot serve. Like for example, you may be able to serve a 12-bit with the 12-bit ADC or even with the 10-bit ADC, a regular motor control application, which is required for say fan or pumps, or even say something like HVAC, heating, ventilation. So, but when you are going for something like a robotics or a CNC kind of applications, you would need a 16-bit or higher kind of a resolution. The accuracy is equally important, and accuracy here would not just as in the ability of the data converter, but also across the different noise conditions, different ranges, dynamic ranges that you have. Is there for a given dynamic range, what basically how well the data converter is designed is quite important. So again, as I said earlier, that we can do a very sophisticated solution on this, but it has to be cost effective and adequate for that particular application when we build, right? And it has to work across the age of the device. It may be a multiple like 100k power on hours, or it could be it depends on whatever is the cycle, and 100k, and certain applications have got a peculiar way. Like if you're putting it in factory automation or in industrial applications, it is a 24/7 working for years, and maybe probably there is a downtime of a maintenance within few months or once a year or whatever, right? But that's a kind of stress that the underlying devices would go through, and it has to sustain it for the given period of time. And finally, the data converters, when you look at how quickly you can convert it. So that comes to the what is the underlying megahertz or the clock that your ADC can operate on. That becomes quite important. Now there is one other part which I have not listed out here, and that is basically how do you present this data to the CPU is quite important. You mean say what is there? I'm just going to present. It's a data, right? It's convert it to the 12-bit or 14-bit. Just put the data out. Imagine you're presenting this this data to the CPU. It has to get an interrupt, come back, read that data, then do the basically processing on it, and then basically do the next step of whatever processing it is doing. Now that conditioning of the data itself could actually give you or you'll have to spend very precious megahertz of your CPU and your system. Now that comes that if you can post-process this data in terms of averaging, in terms of filtering, in terms of comparing with the thresholds, and then giving a refined data out. Not only that, give even the events. Events which basically would say that if it is within this envelope or within this window, trigger an event to PWMs directly, or trigger some GPIO events which will do certain things on a system. Now that kind of actually, if you see, is a performance parameter, not in the conventional kind of applications. This is something which basically you would have normally seen. Yeah, just give it to the CPU, whatever you're sensing, CPU will do it, and then go ahead. But here basically you're saving all that MIPS or all that megahertz or what you have to spend by doing some these applications as required in terms of a regular control loop from your sensing perspective. When you go to the actuation, it is also quite interesting. Here basically what is your resolution again matters, and now you can see the example of a limit cycle oscillation there. If you don't have enough resolution, even if you kind of go close to the equilibrium state, you will keep oscillating around the final state because you're not able to hit the right point. You don't have enough resolution, and which is where how accurately you're able to place the edge of PWM that is going to drive the gate driver and the switch, right? That is very critical. The more precise you are, or more basically the resolution is higher, more than a precision, if it is a resolution is higher, you would be able to get more closer to your equilibrium point very fast. And all the energy that you spend on this is actually a loss, right? And that is one. Also, it may not be able to reach even the final steady state output. So that is what I talked about, the limit cycle oscillations, how basically that accurate. So that brings back to the resolution part of it. The second thing is also about the different types of waveforms. Those are coming in. And now when you say, what do you mean by different types of waveforms? Conventionally, we are doing PWMs in a certain way and trying to control basically the switches. And some of the concepts which were existing and earlier we thought that very difficult to control are now coming back into the applications. Resonant converters were not a vogue if you go about 7, 8, 10 years back. But now more and more resonant converters are coming. So what is the difference from going from the fixed frequency application? Now your control loop frequency could have a variable frequency application to match with the resonance frequency, or get adopt or adjust according to the system requirement. Now that means that you should be able to control. If you kind of come back and convert it to what actually it means from the PWM control, you should be able to control your period very accurately. Same is with the duty. Different type of topologies are coming, be it the dual active bridge and so on. You need to be able to control very actively, precisely, and with the sophistication, different duty cycles. And same is applicable for a phase. If you're doing a multi-phase design, if you're doing basically multi-level inverters, all this basically would require much more better sophistication in your system. And this, if you do not have it on your in your PWM, or if you're not able to build that sophisticated PWM, the stress again goes back to running the CPU at a very high performance, very high clock, and based on that clock you come back. Now imagine if I have to control the put the resolution at the highest resolution, what you can get with the gigahertz kind of a CPU, if you put, which normally you don't, but I think within few years you would, you can go, you can probably still go get to like a PS kind of accuracy, right? Now that basically would means lot of power loss. So naturally, if you're operating something like a 50 megahertz, 100 megahertz, and if you want to control the resolution in a picoseconds, naturally it has to be built in a hardware, and accordingly we should be able to control it with some mechanisms. So that is something which is on the actuation side. When you look at the compute side, it's the most crux of all the real-time control, if you really look at. Now here basically of course it's a math fully or of a different transforms, different filters and so on. So you need a very high efficiency DSP math engine. And I would just kind of give you one point that there was it was a C2000. We actually came back with a floating point controller about 22 or 23 years back. At that time, people were still on a fixed point or trying to still basically do this thing. But now, if you see, everybody has got a fixed point math, fixed and floating point math, right? And people are going from single precision to now double precision. But that is not sufficient. Now for the newer age, when you are going for further next this thing, because if you only have say multiply and add and accumulate those kind of instructions, and then you are say trying to do a complex math, be it your matrix multiplication, you are trying to do the trigonometric operations, unless you have optimized data path which are as inherently built with the CPU than having as a separate data path kind of IP or a peripheral, you would always have some overheads. Like you can always do it as a separate peripheral, give the instruction and get it back, which is a conventional way of doing it. But there are always overhead to write the data, pick the data back, and so on. But if you have something like a coprocessor and all, you can just keep adding the instructions to it. Then basically it would be very much in line, and you can make your pipeline such that those instructions, those special instructions would give you data at appropriate time. Your compilers could be evolved in that direction. And this is something which basically is quite important when it comes to the real-time control, basically the loop frequency optimization and overall the latency optimization. And this is more so with going back to the system trends we saw, where the newer type of switches, the wideband switches are coming and the frequencies are increasing. Go about 3-4 years back, we were still talking about max basically 100 kilohertz, probably 200 kilohertz, and so already now we are talking about a megahertz going to 2 megahertz kind of frequencies for control loop. And that means you have to pack in more, and that packing in more cannot happen just simply by increasing the frequency in that. Now, the other way to look at it is you can do a parallel processing. You can control multiple loops and do parallelly always. But here basically you can see that I'm mentioning here that it is independent control loops. If you try to combine it, there are different type of complications at the system level. We'll see that in a minute when you look at how we are solving it how it can be solved in a multiple ways. And of course, all of this has to have a predictable latency. Like for instance, you can pump in a lot of megahertz, but then basically you have to have some way for memory to match it. Memory speeds are really not matching with the CPU speeds. So naturally, you have to have some kind of a caching mechanism or a mechanism which will basically drive that speed. And that's exactly what basically is done in some of our processors, where we give an emphasis of non-cache based kind of a design, but a lot of custom instructions that you get in here, right? Of course, how you gave a priority to real-time control over the other instructions that we saw, security, safety, those are also of equal importance. Okay, so let me kind of switch the gears now and then basically look at some of the ways how we can solve, and then the comparison with the other will solve. Conventionally, to solve this, what you would have done, you would have just increased the CPU megahertz and then basically taken the corresponding memory subsystem update to get it to the higher performance, which would mean that you would do different levels of memories and different cache systems and so on, right? This is effective in some sense to some of the extent that you can basically do a faster computation with the higher megahertz, and it basically does not put so much of a thrust on improving your sensing, actuation, or other peripherals. They can still remain a very basic kind of thing, and that is one type of microcontrollers you would see in market would try to do it, where the emphasis is go to the next technology, try to pump in more megahertz, keep rest of the things as simple as possible. Now, the problem with that, with the higher megahertz, you're getting into higher dynamic power. And of course, you go to the next technology node, those keep becoming more expensive. And some of the things like your analog and flash, these won't scale in the size. So it keeps becoming more and more expensive. And with the cache, you actually bring in the variability in your latency. If you have if you hit the cache, you have got certain latency number or certain number. If you are not able to hit, there is some exception came in, some different condition came in while you are executing, and then basically your latency is different, right? And that basically is not going to work with some of these applications where you're looking for a precision. You're looking at this time it happens, and rest of the time is allocated for doing some of the other housekeeping and the host functions, the safety and security. So you cannot miss those pulses as well, those periods as well when you are in your system. The second way to do it is do a lot of parallel CPUs. So if you have got, say, you're working on one of the complex topologies, and you have got your device is going to support, say, 2 or 3 control loops, you can actually do that. You can also do different processors, and each processor is also doing, say, the control as well as the housekeeping. So you're actually taking the best out of every CPU. Now, this helps in certain applications. It's quite modular, so you can keep growing in terms of a device with the 2 CPUs and device with the 4 CPUs for different set of applications and so on, depending upon the complexity. But it actually brings in more complexity on the software side. How do you partition the application? What are basically the type of, whether it's a control versus the host, between different control loops? How do you transact and transfer the data? That brings a different kind of complexities in terms of building the application, and not really that intuitive in terms of, or not really that effective. I would say more than intuitive, not effective in terms of when you want to kind of solve with the faster time to market and so on. So of course, when you basically are doing these kind of application, there are different variabilities in terms of if you have say take even on one CPU, if you're trying to do a parallel instructions based, you may have a different pipeline hazards, and if you're doing in parallel with the different CPUs and trying to get some divide a task into multiple, you may get 2 of the outputs at a different time, and the predictability of the task would go for will go for toss, right? One other way is basically what we said, right? Go complete custom, and more you put your sensing. You keep improving the performance. I talked about one example where you do give more sophisticated processed data out. That sorry, was there something? Okay, somebody is okay. So somebody is annotating, so I'm just asking, is there a question? Hello?
I think there is no question, but I'm not sure where the annotation is coming from.
Okay, I'll continue. Probably somebody is somebody's kid or someone is doing the question on that. Okay, so in this case, what would happen is that if you have if you're doing the basically the is there a way to cancel the annotate? Clear. Is that clear? I don't know. Okay, guys, you have to bear with whatever. Okay, I think that's it.
Can the
Okay.
organizer do something? Also, there is somebody with the video on, so would it be possible to turn off that video?
Okay. No problem. Let's go ahead with this, right? So if you have, if you are doing, say, customization on a sensing side, and also you're doing, say, customization on the actuation side, where you have, we talked about how you can build the PWMs, which itself are very rich in the features and functionality and the flexibility they give, and at the same time they are well connected with, say, sensing component, or they're well connected with the processing component, and so right. So that part basically would also work, but and that basically will give you the scalable growth in higher number of endpoints that you can have, and then basically take everything to the central processing. So now more number of control loops are doing, but the processing still has to run at a faster speed in this case, right? And it breaks down the complexity to a good extent in terms of what the processor has to do. But if you're running, say, multiple threads at a some time, it just basically gives you that capability. The only challenge with this is to grow the application, to go to the bigger application. You need to have more such sensing and more such the connectivity will go to the next level. Imagine that you've got 20 analog channels, ADC channels, and 20 PWM outputs. And there is a relationship that you've already set between them in terms of what are the cross triggers are happening, how basically the PWM is triggering the ADC conversion, and so on and so forth. Now, if you have to kind of scale it to the next level and give that give to the say for a 40 analog channels and a 40 PWM outputs, the complexity grows very faster. So that's something which is not very easily scalable. So scalable was one of the factors I mentioned earlier, if you remember, right? So the second thing is, depending upon how basically your application, what is happening in the academia or in terms of the industry, you're seeing that the new type of topologies are coming, new kind of things are coming in the market. So you have to keep updating these at a very continual pace. Though I'm listing that as a disadvantage, but that is something which really comes in. And of course you still have to have some of the things to be passed through the processing, because if you are putting in more complex things in the sensing, like for instance, maybe someone will put a FIR filter or so on his ADC at most. But now if you're trying to build a full say on top of that a trigonometric operations or something very close to this and try to do it, that is going to simply make it very complex. So certain thing has to pass through the processing, and it may not be practical to kind of build with a very light or generic processing all these kind of a system. It's technically possible, theoretically possible, but it's not scalable if you go in a one particular direction. So what am I trying to say with all these, right? It means that when it actually comes to the, sorry, go ahead. Yeah. Is there a comment or question?
Yeah, I had one question.
Yeah, go ahead.
Yeah, is this the same as using an FPGA? Because using an FPGA, one could do these things, right?
No, I think that's an excellent analogy. See, with FPGA, many people are trying to do this today. You're right. This is something, but it's not very, what do you say, scalable in terms of the solutions when it comes to the cost of it. From the cost perspective, it is not scalable, because it's always basically you're going to get the best cost out of it, right? Secondly, with FPGA, you're always bound to what FPGA offers you. Like for instance, if I said that, as I said that you are today doing with this particular setup, you have built a board, you have got FPGA, you have built this, you have got a 10-bit ADC, say, I'm just taking an example, you may have 10 or 12, whatever, right? But you're 10, or you want to go to 12 or 14-bit ADC because you are now same board you want to control, or similar or same FPGA base you want to control, say the say something for the robotics. you don't have that flexibility unless now you have to flip to some newer FPGA and it has to be available and integrated in the FPGA and so on and so forth, right? So I think there is always some limitations of that option, but you're right that this is very similar to going out way to parallel and then try to solve this problem, right?
Yeah.
So
in an FPGA, we can always update the IP, right? If we change the ADC.
yes, yeah. So you can see the analog component is not something which is changeable from what is coming from the FPGA that vendor will give. The PLL, ADCs and comparators that will be given by the vendor. But then basically you always have a flexibility to change whatever is there on the digital side, and that is up to you. Yeah, that processing we talked about, right? That post processing can be changed. Okay, there was some more comment or one more comment there. Yeah. Go ahead. Hello? Okay. I think something is wrong. It was my own voice. Probably this, I was earlier, I thought that it should be recorded presentation. Sorry. So what I was saying with all this, right? What I was saying this is that if you take one approach, one type of approach, either you increase the megahertz or you do with the parallel CPUs or you get a very high node processing, you may not basically be able to get the solution, because each of these has got a pros and cons. Like for instance, if you do megahertz increase or one side of it, you may be able to meet a predictable latency, short-term predictable latency by doing some of the hooks, but you will either increase in the complexity or in the cost or in the power, right? And if nothing else, you would have a very high amount of change that you have to continuously do on your customizations, which means that very high development cost. And when basically in industry, how normally it happens is that you stick to one device and you probably stick to it for multiple years, so that your development and in terms of the investment in your training your engineers and getting basically the outputs out of it kind of remains constant, right? So those are some of the factors which really impact these choices. So megahertz, as I said, will increase the power, and as well as weight states will basically that basically will be kept in a limit if you really increase the megahertz, but then basically it has got a power increase. If you take the CPU parallelism and across the independent functions, then basically the way you should do it is you make it such that you separate out the control function and you separate out the host function in a different bucket, right? Then basically if you go to the standard functions that you embed with the node, keep them very commonly used functions like averaging, min max, common filtering of the sensors, and a sophisticated PWM. So there is some balance that has to happen from all these three knobs to basically kind of get to the final thing. One of the key thing, as I mentioned, that going directly from the sensing to the actuation is quite important, and that is something which or from the sensing to the process data to the sensing, or PWM being able to do something on its own. Those are very important as far as this two-piece control. So finally, to summarize, we looked at, say, precise sensing and basically the predictable latency. That is something very key. And of course, the actuation, which is flexible for real-time control. We also saw that present-day trends are driving for the higher power density and higher efficiency, as well as the cost and other factors are always there going to be impacting. And there are multiple knobs you can take which are common with the rest type of processings, but pushing in one specific direction will violate some or the other vector. So you always need a balance of these megahertz, parallel cores, as well as the smart sensors to drive the optimal real-time performance. So that is what I want to summarize and stop at. I just want to take any more questions are there and probably open it for discussion. Yeah, go ahead, Pritam.
Yeah, so I had a question not related to real-time control, but system design. So you mentioned that higher frequency and power control and higher power density. So how does it
Correct.
affect the EM interference and noise in these systems? Because definitely, I think even the real-time control systems also are getting more and more dependent on the network, and the voltages at which these memory buses as well as the devices are operating are lower, so their noise tolerance is not going up, right? I'm not very knowledgeable on this error correction mechanisms in, say, communication protocols or the buses, but it would definitely be more susceptible, right?
Yeah, no, that's very valid point. They are susceptible, and we have basically we are more and more going towards that interfaces, especially if you talk about the communication. Uh, we will be looking at some things like end-to-end communication, where basically you have the messages which are there have got enough integrity checks. Even see, one of the things that where it is quite important that on a real-time control, when basically we try to design it, we're trying to keep the megahertz as low as possible as far as our design is concerned, but at the same time trying to give the higher control loop frequency for that. But said that you have generally a higher trend towards the higher frequency. You have the other components, be the RF or other EM components which would be there, which also are going to sit very close to this system, and that impacts not only just the communication but even to sometimes the memories inside. And this all will come back into that bucket of what you already talked about, the safety bucket, right? And that is basically adds additional overhead as far as the cost is concerned, in terms of always have a ECC for your memory, have packets which are sending either they are sent with the CRC, or they are sent with basically some other checksum that is embedded with it. So it brings in additional cost, additional basically the overheads in terms of the throughput as well as in terms of the cost to it. Yeah, you're right.
Thanks.
Okay. Was there someone else hand was raised? Let me just look at it.
Yes,
Anybody
yes,
else?
Dr. Shailesh, may I ask a question? I'm Joy here.
Yeah, go ahead. Go ahead.
Yeah. So, would it be fair to say that given the constraints that current systems are imposing, the only way to do real-time control is to implement the algorithms in hardware?
Very good question. I won't say that it's implement everything into the hardware because there is enough amount of what do you say the churn in terms of newer techniques and newer methods. Those are coming. What is key? What is key is to identify the common what do you say common operations. Like I mentioned that if you are doing, say for instance, all of these power conversions, if you take, you are doing some sort of a three-phase control, and you're going for some kind of a transform, say that Clark transform, part transforms you're doing, that basically you're getting from three-phase to single phase and so on. So you really look at it, it's a metric operation, it's a trigonometric operation. If you're able to pick the knobs out of the basically the basic operations out of it, and then put them in a hardware such that basically those can be used, then that would give a thing. But if you try to kind of unroll the thing and put it, you will be very much locked, and that is not a very good for the ASIC development per se. It is good for the FPGA development. Somebody earlier was saying that for that it is really good. And today in industry, there are people who are in a lack of certain ASICs, means whatever they are using, or even 2000 at places where they are using, a lack of adequate number of customizations. People are going with the FPGAs. But as far as development is concerned, you want to pick the pieces which are very key, and then basically take them as a customization, as basically a generic instruction.
Okay. Yeah. So the identifying the key pieces is important. Otherwise, if you if you do something in hardware and then things change, then there'll be a problem. That's the
absolutely. Like for instance, I'll tell you, right? Some things are basics, right? As far as the trigonometric operations are basics, the type of filters are basics, and you many of the MCUs today they are doing it. Matrix operations, how efficiently you can do the matrix operations, and of course it has to be predictable. If there is a null matrix, so it takes a lesser time, and if there is a matrix with some elements populated, it takes more time. You can't have that. You have to have predictability on that also. So how you can provide that predictability as well as efficient matrix operations, that becomes important. So some of the fundamental pieces won't change, but you're right. Like for instance, I'll give you an example, right? A few years back, we were actually doing something called as a nonlinear PID. We wanted to develop the proportional derivative loop, and for that there's a problem of implementing it around the zero. Around the zero, the error is really high. So we wanted to implement that, and we thought about different way. But finally, after all the analysis, we came back and say that in all these applications, ultimately there will be two instructions that you require: a log and power. Now, log and nobody builds it into the instructions, right, of the CPU. But we said that go ahead and put this as a coprocessor. If I do that, that will basically solve it. So it comes down to that ultimately where basically you draw that synthesize and bring that instruction back. So you're absolutely right. You have to be that basically brings to how well you can analyze it and bring those instructions in. Yeah.
Right. Okay. Thank you.
Yeah. Okay. So any other question?
Maybe one quick question. How important is it to use an RTOS for such systems?
Well, that's a good question. On the RTOS is becoming very well important on many of the newer applications with basically specifically in a systems where the safety and those kind of applications are involved. Especially you have this automotive or so, and you want to have a timed events, very well precisely timed events that you want to have. Most of the MCUs today support RTOS, but as far as when it comes to the control loop, what is important is is basically the highest priority to the control operations. You cannot have RTOS deciding on, oh, this is a time slot I will give it to control, and this is the time slot I will give to communication, because you may burn the motor down the line if you don't give the priority to the control application. So that is where even if you have the control taken into the RTOS, it always has the highest priority, and all other threads run below it. Means they come below it. So irrespective of whatever is the time slot for whichever thread, control has to run at the master or at the top. Yeah. So there is it's not really control today. RTOS is not so much used for the control piece of it, but as I said, there are a lot of other housekeeping and the portions of your the safety, security, all these are included, which periodically keep happening. You have to keep the pulse, you have to keep checking that, you have to keep diagnostics, those kind of things. Definitely RTOS is very good for this. Yeah.
Right. Thank you.
Yeah. Okay. Are there any other questions or any other comments or observations?
So one point I wanted to ask as a general trend, so related to Professor Kuri's question. So as against like doing some things in software versus hardware, is it like the analog versus digital, in the sense that are the analog skills kind of dwindling and finding it difficult to find people who are good at doing analog designs for implementing some of these integrations and actuations?
No, actually, you ask it very interestingly. Actually, it's not an analog versus digital divide. Really, one of the things that analog is still very useful, basically on some of the when you have a very specific or a limited variability in what you're trying to do. Okay, analog in the end, when you lay out the analog, the degree of freedom is limited, because you would say that this is the range of voltage, this is the range of this is the variability I will give, and within this gain or within this bandwidth I will support it. Now that is one thing. And if you really look at the digital part of it, is basically allows you the scalability to use the same controller at multiple places. Now, when it comes to the integration, you are right that whether analog or analog or digital, you need to have basically this as a skill set, you need to have it across whoever is developing it. But it's really not what type of solution. The solutions are today, even conventional, there are many solutions still on the analog. More and more where basically, as you might have sensed it, that more and more where basically there is a higher performance need in terms of scaling it to the different higher frequencies to operate, or basically higher bandwidths or to support. There people are moving to the digital because it's easier to control that way. And tune it, change it at any time. So that is what is happening. As far as the skill set is concerned, see, even to develop the microcontroller or the analog of it, you would need whatever is needed for any other analog design that is needed. At a system level, yes. At a system level analogs skills in terms of solving a control loop and other things, which basically is something will remain always a niche. And certain applications still today need the analog control to be supported. It's not that analog is going to go anywhere. It's only that it depends on it's more of a business side which will drive the digital more because of the scalability and other things. What you can solve in digital, you can solve probably in analog as well with the right component. The only thing is that it is not scalable. That's the problem. It's not widely scalable, I would say. Yeah. Cross. Does it make sense?
Yeah, thanks. Thanks for the perspective.
Yeah. Okay. So hope this has kind of helped in some sense to you guys. I really enjoyed talking about it. And if there are any other questions, get back to me through the coordinators. And yeah, thanks a lot for the opportunity given.
Thank you.
Thank you, Mr. Shailesh, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the web page. Thank you and have a great evening.
Okay. Thank you.